Last video lecture we learnt about the normality assumption of the error term ui. When we make this additional assumption, the model that we get is called the classical normal linear regression model. We also looked into the advantages of making this normality assumption, and we said that the properties of the estimators that are derived based on this normality assumption will help us for hypothesis testing. So now we are going to look into interval estimation and hypothesis testing. So, like I said earlier, the OLS estimator beta 2 hat is a random variable. The reason we call it a random variable is that it is based on sample observations. So every time your sample changes, the value of beta 2 hat will also change. And our assumptions ensure that the mean value of the beta 2 hat when we take repeated samples will equal to the true population parameter beta 2. The reliability of the point estimator beta 2 hat is measured by its standard error. Standard error is the same as standard deviation of the variable beta 2 hat, right? Now, there exists another method which says that instead of relying only on the point estimator, we can construct an interval around this point estimator. Which has, say, around, with the probability of 95% confidence, we can construct an interval around this point estimator which may include the true population parameter beta 2. So, we can construct this interval estimator only if we have an idea about the distribution of the point estimator beta 2 hat. Technically speaking, in interval estimation, we are trying to find out two positive numbers. The first is alpha, which represents probability between 0 and 1, and the other is delta. So, we are trying to construct an interval that ranges from beta 2 minus delta to beta 2 hat plus delta. And we are saying that we have 1 minus alpha percentage probability that this random interval will contain the true population parameter beta 2. The interval estimate constructed can be written in this manner, equation 1. Here the interval beta 2 hat minus delta to beta 2 hat plus delta is called the confidence interval. Alpha is the level of significance. Generally, we use 1%, 5% or 10% level for alpha. These are the widely and commonly used significance levels. And 1 minus alpha is the confidence coefficient. Is called the confidence coefficient. So if I assume that my alpha is 5%, so when I'm trying to build this interval estimator, I'm saying that there is 95% probability of successfully constructing an interval beta 2 hat minus delta to beta 2 hat plus delta, which contains the true population parameter beta 2. There are a few points that you need to keep in mind about this interval estimator. The first and most important point is that I am not saying that the probability of beta 2, true beta 2 lying within this interval is 1 minus alpha. Okay, so I'm assuming alpha is 5%, so that 1 minus alpha is 95%. Okay, so I am not saying that the probability that the true beta 2 is within this constructed interval is 95%. No. Once the whether the beta 2 lies inside the interval or not, if it lies inside the interval, the probability of beta 2 being in the interval is 1. If it does not lie, the probability is 0. So this probability of 95% is associated with the construction of the interval. So I am saying that the probability of constructing a confidence interval which contains the true beta 2 is 95%. Or in other words, I am saying with 95% confidence levels, we can construct successfully a confidence interval which contains the true beta 2. So probability is not associated with the possibility of beta 2, true beta 2 lying inside the interval or not. The probability is associated with construction of this interval beta 2 hat minus delta to beta 2 hat plus delta. Okay. Another point that you need to keep in mind is that beta 2 hat is a random variable. I say that it is a random variable because it varies from sample to sample. If your sample changes, your beta 2 hat value will also change. So it's a random variable. And since my interval is beta 2 hat minus delta to beta 2 hat plus delta, even this interval defined in this manner is a random interval. This interval will also vary from sample to sample. Now, because this confidence interval is random, what does a probability of 95% mean? It means that if I continuously take sample after sample after sample, calculate the beta 2 hat for each sample and construct a beta 2 hat minus delta to beta 2 hat plus delta, that is I construct confidence intervals for each sample, then I am saying in the long run, on an average, 95% of the total number of cases or total number of samples will contain the true population parameter beta 2. I am saying 95% because I have assumed alpha is 5%. Okay, so I am saying if I say 100 times I take sample from a population, I will calculate beta 2 hat for each sample. I will construct a confidence interval for each sample. So out of this 100 times, at least 95% of the cases in the long run will contain the true population parameter beta 2. So again, the 1 minus alpha probability is associated with the construction of the interval. It is not associated with whether beta 2 is inside the interval or not. Okay? Now, I know that beta 2 hat will vary from sample to sample. But once I have selected a sample, for that sample, my beta 2 hat value is fixed. If my beta 2 hat value is fixed for the sample, then the confidence interval based on this beta 2 hat value will also be fixed. So once a single sample has been specified, it will have a single beta 2 hat value and it will be associated with one and only one fixed interval, confidence interval. Okay. So in a specific case, once you have created a specific fixed interval, confidence interval, whether if the true beta 2 is inside the interval, we are saying the probability is 1 of beta 2 being inside. If the true beta 2 is not inside that fixed interval, the probability of true beta 2 being there is 0. Okay. Now, that was the logic of constructing the confidence interval and what it means, what the probability of constructing an interval means. Now, how do we actually construct the interval? What is the step-by-step process? Right? So, we know that under the normality assumption of ui, the OLS estimators beta 1 hat and beta 2 hat will also be normally distributed. So we keep taking the example of beta 2 hat, right? So if we have calculated a beta 2 hat variable, you can construct, which follows normal distribution, you can construct a variable called z, which is beta 2 hat minus its mean divided by its standard error. When you do this transformation, your variable z follows standard normal distribution with mean 1 and mean 0 and variance equal to 1, right? So if everything is fine and all the values are known, beta 2 hat minus population beta 2 divided by standard error of beta 2 hat can be written as this equation. So standard error of beta 2, if you remember, is root of sigma square, where sigma square is defined as one second, right? So standard error of beta 2 is defined as sigma square divided by summation xi square. This is the variance of beta square. So standard error is its square root. So if I take square root, that means sigma by root under summation xi square, right? So if I can construct such a variable called z, it will follow standard normal distribution, mean 0, variance 1. But what happens is, this variable sigma is associated with the population, and the population sigma square, or the population variance, or the and population standard deviation is usually not known to us. So what happens? We are forced to use its unbiased estimator, sigma hat square. If you remember from previous lectures, we had studied that sigma hat square is summation ui square divided by n minus 2. So this is the sample variance. The sample standard deviation will be the square root of this sigma hat square. So because we do not know the population sigma square and are forced to use its unbiased estimator sigma hat square, the statistic that we can now create takes this form, right? Instead of sigma in the earlier equation, I have written sigma hat, but the distributions have changed. My beta 2 hat still follows normal distribution, but sigma hat, or rather sigma hat square, if you remember, follows chi-square distribution with n minus 2 degrees of freedom. Remember, we had said n minus 2 times sigma hat square divided by population sigma square follows chi-square distribution. There is a statistical theorem which says that if you, in the numerator you have a standard normal variable and in the denominator you have a variable whose square follows chi-square, the ratio of these two will follow a t distribution. Okay, so it's a technical thing. You don't need to really go deep into it. So you can just understand that because we do not know population sigma square, we are forced to use the sample sigma hat square. So when you use the sample value sigma hat, my variable that I have constructed, or the statistic that I have constructed, follows t distribution with n minus 2 degrees of freedom. Okay. How do I construct a confidence interval for this? If alpha is my level of significance, a confidence interval will be minus t alpha by 2, and the upper confidence limit will be t alpha by 2, where if alpha is 5%, so my critical value minus t alpha by 2 will be t at 0.25, that is at half the percentage, half of 5%. And similarly, t alpha by 2, the upper limit will be t at 0.25. This can be read off from the t distribution tables. This is the part that you have already covered in your quantitative techniques paper in first year of PG, right? So now instead of t, if I replace in general terms, that is t is equal to, my statistic t is equal to beta 2 hat minus population beta 2 divided by standard error of beta 2 hat. If I replace this formula over here, I can adjust it to form this formula for the confidence interval of the true population parameter beta 2. So with 95% confidence level, I can say that this interval may contain the true population parameter beta 2. Similarly, I can construct a similar interval for beta 1 as well.